you're looking for a video and it's not showing up, send me an email. Unfortunately, it's not a very streamlined process for getting these videos online. It's a multi-step thing, and occasionally I'll forget one of the steps along the way. So just let me know if there's a video missing. Your next homework is due on Wednesday, which is the same day that we are going to have our midterm exam. So that's 2 days from right now. You should bring your computer because one of the questions on the exam, you're going to use Excel for that. And honestly, I haven't written the exam yet, so I can't give you any hints on whether that's likely to be a pipe diameter sizing, or 3 reservoir, or a loop problem. I honestly don't know. So I don't know. I don't know. No, I've got a 3-sided coin that I flip, and I'll just choose from that. Yeah. So you can bring a 1-page equation sheet with you. I'll provide the equation sheet that's posted on Blackboard. And then one other new announcement, class on Friday of this week will just be a recorded lecture video. So we won't meet together in person on Friday. So there's no new material today. Well, sort of. It's a callback to some of the stuff that we've looked at so far. We're going to talk about the design project that you've got this semester, and I'm going to do a brief demo of how to use the WaterGEMS software. So before we start on that, do you have any questions about these announcements?
The exam's not covering homework 6, is it?
Yeah, it is. Yeah, it is. Yeah. The exam is covering the concepts from homework 6. All right, let me pause this recording while I hand out. Let's talk about this map. So what I'm showing you on the map is a hypothetical land development project. Let's just say that there's some raw land in a certain city, and each of you is going to be assigned a different city for reasons that you'll understand in a few minutes. But there's some raw land that's going to be turned into a community that includes, inside this north zone, the community is going to have both residential and commercial properties. It's all mixed together. In the south zone is only a residential area. Over here in the east zone, there is a hotel, a food processing plant, a mall, and then there's a sports stadium you can see that's to the north of the community. Here's a cardboard box factory, a housing project, a golf course, a hospital. So what this project is all about is figuring how large should the pipes be to take water from the spring. Up here around the 300 is a spring where water comes out at a constant rate. You're going to have to put a reservoir somewhere on this hillside. By the way, these curved lines, those are contour lines. It tells you the elevation of the ground at any particular location. So you can see that this is a big hill and that the land is sloping in this direction towards the cardboard box factory. So the project is that you're going to do an analysis based on some parameters I assign. Each of you will have different parameters. For example, one person is going to have a population density in the south zone of 200 people per hectare, whereas another person will have population in the south zone of only 25 people per hectare. So you're going to have wildly different water demands when you have maybe a 10-fold variation in the population density. By the way, hectare. Maybe you're not familiar with that. What is 1 hectare? Anybody know?
10,000 meters cubed.
Very close. 10,000 meters squared. Yeah. So 10,000 meters squared. So what it is it's 100 meters by 100 meters. That's a hectare. On your map, down here at the bottom, there's a scale. And if you have a ruler with you and you measure the length of that line, what you'll notice is it's 1 centimeter. And so that gives you a way of estimating distances on this map. It's a scaled map, print out to scale so that you can measure, for example, what's the area of the south zone. And so if you know the population density in the south zone, 200 people per hectare, and then you measure the area in the south zone, you can find out how many people are living in the south zone. So the overall thing that you're trying to accomplish is sizing of the pipes. And how big should the pipes be? Well, that depends on how much water the people are going to use in the south zone. So now you have to start thinking about what's the relationship between people and water use. And we'll talk a little bit about that today. And it's also going to be the subject of some of the research that you're doing. People use water differently in Boise, Idaho, for example, than they do in Miami, Florida. There are climate differences. There's differences in the behavior patterns in people from place to place. People use water at different times in different ways. And so you're going to have to do a little bit of study of those locations and assess how there may be some unique characteristics of the way water is used at those locations. So each of these green arrows represents a place where water is going to need to come out of a pipe network. So remember, what I've said is that there's a spring which feeds water to a reservoir. So somewhere on this hillside you're going to put a reservoir. And the reservoir is connected to junction A. And then from there water flows to each of these other locations. Now this black line, that represents the city limits. That doesn't represent where you have to put the pipe. So for example, if you're going to be connecting junction C and junction E together, there's no reason to follow the city limits to take that pipe from C to E. In fact, that would maybe be a waste of money because there's no reason for a water pipeline to be over here at the northeast corner of the city limits. You only need to deliver water to these green arrows. So part of your project is trying to identify like what's the most optimum pathway for the water pipelines to take. Part of your design project is trying to figure out how big should the pipe diameters be. Should you put in a 100 millimeter pipe between A and B? A 750 millimeter pipe between A and B? Well, you know, a 750 millimeter pipe is not likely to have very much head loss, and so it would be really good at ensuring that you have high water pressure at B. But that big diameter pipe is also very costly and maybe not necessary. So you're going to go through this process of iteratively optimizing the pipe sizes, which means you're going to be changing the pipe diameters over and over and over to try and find out what's the smallest pipe size that you can get away with at each of the sections in the network to provide the minimum pressure under the demand condition of maximum flows. So that's at one side of your design optimization, is you have to have at least a minimum pressure on the day where it's really hot, so everybody's using a lot of water. The design condition assumes that it's either this peak hourly demand or the peak daily demand plus a fire is occurring simultaneously. And this is talked about in the demand summary sheet that I'm going to give you. But at maximum flow rates, you still have to have some threshold floor of 240 kilopascals of pressure. That's the lowest your network can go. And the highest your network can go is 850 kilopascals. And you're going to see that in your pipe network at night when people aren't using much water, so that there's very little in the way of head losses. So what pressurizes the network? Well, it's where you put the reservoir on the hillside. If you put the reservoir really high on the hillside, that's going to deliver a large pressure to junction A. If you take it too high on the hillside, then at night, when people aren't using much water, the static pressure in the network, meaning the pressure at zero flow rate, is going to exceed the maximum of 850 kilopascals. So it's this balancing act, not only of, you know, where's the right place on the hillside to put the reservoir to get that optimal pressure, but then also how big should the pipes be. All right, so the project is broken up into three main phases, and you have 3 draft submissions over the course of the semester. You'll notice on the handout that I've given you, it shows the deadline for each of these different phases. And your first submission, the demand forecasting portion, is due on Monday, March 6th. So that's a pretty quick turnaround. I think, what is that now, 3 weeks from today? Or is it just 2? 2, okay, that'll be plenty of time.
It's on our capstone project.
Well, this is more important than capstone.
It is.
Yeah. Way more important, yeah. Just tell Dr. Michelson I said that too. All right, good. So the first part of the project, what you're going to be doing is some sort of an assessment of how much water is needed at each of these junctions. The second phase is how big should the pipes be and what size should they be. And so for part one, it's just hand calculations. Part two is you're using the design software, WaterGEMS. And part three, you're using Excel to size the reservoir according to a process I'll show you in a couple of weeks. So the first submission, Monday, March 6th, is the hand calculations for demand estimation. Part two, which is the network pipe sizing, is Friday, March 24th. The reservoir sizing, April 3rd. And then the final submission for the project is due on Monday, April 17th. So what I found is that by instituting these intermediate submissions, students do much, much better on the final project, like the final report. And so we're kind of forcing you to break this project up into bite-sized pieces instead of leaving it to the very end. It eliminates some of the confusion that could arise otherwise.
You get feedback for every...
I do. I give you feedback after each stage. And my goal is that I'll give you feedback on your demand estimation early enough that you could incorporate that into your pipe network sizing. So sometimes, for example, people misunderstand what I mean by high density housing. That's one of the things that you have to provide water for. And high density housing, that means like a dormitory, the kind of place where you've got a lot of people. It's similar to apartments, but like taken to the extreme, like an apartment with 4 people in it. So just really high population density. So sometimes someone will make a bad assumption, for example, about how much water is needed at the golf course. Like a common mistake there is they assume that the water is going to be delivered to the grass, because that's the main thing that you need at the golf course is providing water for the grass. People don't think about it, and they're doing their calculations. They know the volume of water that's required, and then they say, well, there's 24 hours in a day, so just divide the volume that's needed by how many seconds are in a day. But they don't think, well, you can't leave the water going when people are golfing, right? The water can only occur in a smaller period than 24 hours per day. So I'll give you feedback on the demand estimation, hopefully early enough that you can incorporate that into the pipe sizing. Okay, so let's talk a little bit about demand estimation. And one of the things that you should be aware of is that people use water at an unsteady rate. Even if you know the volume of water per day that you consume, like an average in the United States is about 220 liters per person. That's the daily usage, but you're using that not at a constant rate through the entire day. You're using it maybe very little at night and much more during the morning and evening peaks. And if you kind of combine a big population of people, where some people will take their shower at 7 a.m., some people take a shower at 8 a.m., some people will be doing laundry at 6 p.m., and so on. The typical trends is that there are 2 peaks per day, and this is showing the maximum day for the year and a typical winter day when the flow rate demands would be even less than the average day. So 100 here represents 100% of the average day. So the 2 design conditions that you have to consider in this demand estimation is what's the demand for the maximum day, and then also what is the demand during the maximum hour. So the maximum day is about 1.8 times the average daily flow, and the maximum hourly demand is 3.25 times the maximum daily demand. So average day, multiply it by 3.25, and that gives you the maximum hour. Average day multiplied by 1.8 will give you the maximum day. So in your project, you're going to be designing each pipe so that in each of these arrows, you're going to identify what's the larger of either the maximum day plus fire demand or the maximum hour. And the larger of the 2 is what you're designing for. maximum hour or maximum day plus fire. Now, it's all going to be summarized on a table. Let me give you that now. I'll bring it up on the screen here, what it looks like. Do you have a question?
Yes, could you maybe recommend us make copies of this? That way, if we wanted to try different iterations or different numbers, we can have more than one template to go off of.
This is posted on Blackboard, so if you need to print out extras, you can. But when you change your flow rates, you won't necessarily have to change what's written on here. Like what you're going to be iterating is the pipe size, not necessarily the flow rates. I mean, you'll maybe have version A and version B of your flow rates, but you probably won't have a lot of different versions of your flow rates. What you're going to have a lot of different versions of is the pipe sizes that you use. So if you look at the way this is set up, it's set up so that, for example, in the north zone where there's both residential and commercial areas, you're going to find out what is the average daily flow rate in liters per second. And then the peak day would be 1.8 times the average day. The peak hour would be 3.25 times the average day. And then up here at the top is where you carry over the fire flow that's defined in your specifications handout, which I'll give you in just a moment. So peak day plus fire. And then the larger of the two is what you'd combine with the commercial demand to put into the design flow rate. So like the width of these kind of implies whether or not you're supposed to be adding together the peak hour and the peak day. So for example, in the south zone, it should be the larger of the peak hour or the peak day plus fire. So the width of this covers both of those columns to help you just reflect on the fact that you're picking the larger of the two. There are certain things that are peaked according to human behavior, like the hotel demands. You'll notice that there's an average day, and peak hour. But the food processing plant, you don't do any kind of peaking factors for, because I'll tell you in the handout that the food processing plant is using a certain volume of water each week. And so you just need to figure out what is the flow rate that they're going to be using according to how often the number of working hours per week that may apply to the food processing plant. Shopping mall is about human behavior, so it has peaks. But then the sports stadium, you're going to have to, I just tell you the number of seats in the sports stadium, so you're going to have to do some research and just logical thinking about what do they use water for at the sports stadium. And maybe they use a little bit to water the field, but I think more of like how big should the pipe be out to the sports stadium depends on like halftime. Like how many toilets are flushing at halftime, or how many people are taking a drink of water, or how much water demand is there for the food prep at like some certain key moment of the game. So I think that's what you have to keep in mind is at each of these locations, how is water really going to be used on this peak day, which is the worst case scenario that we're planning for. We want to make sure that the pipes are big enough to deliver water everywhere in this city when it matters the most, which is a day where there could potentially be a fire. It's a really hot day. They're watering the golf course. The box factory is going. People are at the shopping mall. The food processing plant is operating. Everything's happening all at once. We want to make sure that we can maintain at least 240 kilopascals throughout the network during that design condition. Let me give you the parameter assignments now, and I think this is going to be the last handout I give you related to the project today. You'll notice your name on a certain row. And then across the top are the parameters along with units. At least I hope everybody's name's at the top. If you notice your name's not on the list, let me know and I can make an assignment for you, but I think that they should all be there. Okay, so for instance, you'll notice that in Sacramento, so the top row there, Sacramento, in the north zone, we're assuming that he needs to provide 15 liters per second for fire flows. The population density of the north zone is 20 people per hectare. And so from that, he's going to have to know what's the area of the north zone, you know, using a ruler and some measurements there. And then he's going to have to do some thinking about what's the relationship between the number of people in a residential area and the water demand on the average day. So how many people are there and how much water is used per person per day. Commercial, the same area times the population density for commercial will tell you how many people are in the north zone doing commercial type things. That means that they're at like shops or in office buildings. You can think of it as maybe they're at work. So here for the hotel, you know the number of guests. So you'll have to ask yourself, you know, how is water demands for people in a hotel different from water demands in a house? The food processing plant, it says here it's mg per week. Mg means million gallons. So you're going to have to do a little bit of a units conversion there, because I'm telling you, for instance, that at this food processing plant in Sacramento, they're using 5 million gallons of water per week. So you need to convert that to liters per second, because on the summary table, everything should be expressed in liters per second. And so another part of it is going to be thinking about the food processing plant. This is like a place that people work, and so it's not going to be open 24/7 necessarily. I mean, maybe it is, but the conservative design estimate is that all of this water, this 5 million gallons, is used maybe during a 40-hour work week. And so we want to make sure that the pipe network's big enough, so in each case we should err on the side of conservatism. So we assume that the water is being used over a relatively narrower period of time. So you'll notice it says how many stores are in the shopping mall, the seats in the football stadium. So there's some parameters here that are going to be inputs that you use in trying to estimate the amount of water that's being used. So let me show you one of the resources I've just loaded onto Blackboard today. It's an example of the type of data that's available. Now the data that I'm going to show you it's old. It's from a source that was published in the mid-'80s. So it's old, and it's just kind of like national averages. It's not applicable specifically to Sacramento or San Diego. You could probably find a lot of the same data that is specific to a particular town. But like, for instance, this shows, typical water use. It shows that the typical domestic water use is 220 liters per person per day. So that's just a nationwide average. So like in your project, if all you did was just use the data in this provided handout, you can get okay results doing that. But if you want to get good results, and good grades come from a good result, if you want like better grades and better results, then you should find out, like for instance in Sacramento, what's the average daily water use for residents in Sacramento? Is it more or less than 220 liters per person per day? For instance, here's a breakdown of where that 220 liters per person per day comes from. You can see how much of it is toilet use, drinking, clothes washing, and so on. It's kind of interesting to see the breakdown. But again, this data is relatively old. I think it may even predate low flush toilets, and so the breakdown could have shifted over time. It's got some information related to commercial facilities, and this type of data may be useful when you're thinking about like office environments. How much water is going to be used by people in an office? So you can see here it's per employee in an office. Between 30 and 65 liters per person per day, with a typical value that's also provided. It's got restaurants, department stores, shopping centers, and so on. So this is just, I think, to whet the appetite, to make you aware of what kind of information is available. And what I hope you do is find something more recent and something more geographically applicable to the city that you're assigned. Hospital, prison, rest home, and so on. Recreational areas, country clubs, movie theaters, swimming pools. All right. So any questions so far about this available data? So what you need to do between now and Monday, March 6th is fill in this table and have supporting calculations, supporting justification. The submission for part 1 is hand calculations, including this summary sheet at the front of the hand calculations, as long as a written typed narrative that explains, like, what is the data sources that you identified, what is your rationale or justification for certain assumptions that you've made. So for example, explain to me how you figured out how much water is needed at the golf course. Like for your town, whether it is Albuquerque, New Mexico, I instruct you in the handout to go and find some weather data related to precipitation in Albuquerque, New Mexico in the driest month of the year. And so make up the difference between the rainfall that occurs and the 1 inch per week that's needed by the grass. That's how much water you're going to have to apply at the golf course. So in the written narrative, explain to me, where did you find the data about precipitation in Albuquerque? What are some of the assumptions that you made? For example, the number of hours per week that the water is applied at the golf course. So just kind of walk me through, in written terms, the calculations that support this table. Okay, so any questions? Go ahead.
So the table doesn't include the rainfall assumptions?
Well, the rainfall part of it goes into how much water is needed at the golf course. So there's no place on the table where you're actually going to write, like, how much did it rain in Albuquerque, but it's going to be reflected by how much water you use at the golf course. So that's a good point. There's a lot of things, that intermediate calculations and stuff, that won't show up on this summary page. The summary page is really about trying to figure out how much water is needed at each of these junctions in the network. So for example, the north zone, look at which arrows feed water into the north zone. It's not B, it's not C, it's not L. A and M are the junctions that feed water to the north zone. Just A and M. So when you calculate how much water, like what's the amount of water, liters per second, that's the design flow for the north zone, you'll divide that by 2 to figure out the design flow rate per outlet. So you assume that half of the water consumed by the north zone comes out at A, half of the water consumed in the north zone comes out at M. So the summary sheet is mainly to set the stage for part 2, which is when you're going to be sizing the pipes in the network. Are there other questions? As questions occur to you, you can send me emails, or we'll have time at the beginning of class to spend a few moments addressing conceptual issues if you've got them. If you want to ask a question about the project, then we certainly can. Let me show you this tool that you're going to be using for the pipe sizing. How many of you have your laptop with WaterGEMS installed today? Many of you. That's good. So fire it up if you do. If not, you can just follow along, because we're going to look at a pipe network together. I'm going to show you how nice it is when you don't have to use the loop method. I mean, you know the loop method works, but it sure is tricky sometimes to get every minus sign in the right place and click in the cell location just perfectly. Okay, so this is the pipe network we're going to analyze. I've just handed it out to you. This should look familiar. I think we've analyzed this network before using Excel. There's just one small difference though. What I've done here is I've said, let's assume that there is a reservoir connected at A with the head of the reservoir at an elevation of 61.162. That will cause a pressure of 600 kilopascals at A. And then the other location we had water going into the network was at D. And so to make that possible within WaterGEMS, we have to connect another reservoir to make sure that there's a place that the water can be coming from to enter at junction D. So that's what we're going to be replicating here in WaterGEMS. Now, this computer that I'm working on right now has WaterCAD installed, but it's visually indistinguishable from WaterGEMS. And WaterGEMS is the one that you should use. I'll install WaterGEMS on this one in the future, but just for now it's got WaterCAD. The only difference is that WaterGEMS you can have a lot more junctions compared to WaterCAD. It's limited. I think WaterCAD has enough junctions that we can do this example today though. So when you start the program, in order to start the program, you have to have the connection client working down here in the system tray. So this, you have to be logged in to the connection client, otherwise you won't get the WaterCAD or WaterGEMS software to start. But once you start WaterGEMS, click Create a New Hydraulic Model, and I'm going to maximize the screen so that it takes up all of the space. Okay. So we're going to draw a schematic representation of our pipe network. It won't be to scale where I'm drawing. And that's one difference between this basic example I'm showing you today and your project, is in the project I've given you a scaled map that you can bring up in the background and you can draw on top of the scaled map so that each of the pipes are the correct length. Here in this basic example, we're just going to draw a schematic representation of the network, and then we'll go in and manually correct the pipe lengths a little bit later. So here across the top in the ribbon, there's this layout button. And if you click on the layout button and then bring the cursor down into the main menu, you'll notice that the pointer has changed. And so right now, that is the symbol for a junction. And so I'm just going to click in some location, and that's going to be junction A. Move some distance away. That's junction B, C, D. Here is F, E. And now I need to click over to what's C again. And now the escape button, because I'm done drawing over on this side. So if I do the escape, then it'll stop drawing. And I need to connect junction F and junction A and escape. Okay, so you'll notice that's all crooked and messed up, and if I clicked on any of these pipes to find out their length, it's not going to match what it says on the paper, but we'll get that sorted out in just a bit. The other thing I want to do is add the reservoirs, and so if you right click, it's going to change from junction to reservoir, and then just click in some location that's adjacent, and then right click again, back to junction, and connect it to junction 1, which is A. And then we need to add the reservoir over here near D. So reservoir by D, right click again, back to junction, and just connect the dots over here to this junction 4, which is really D. All right, so we've got a pipe network. Water comes into the network through these reservoirs. And to make things a little bit easier, maybe I should rename the junctions. you know, because it's called A, B, C, and so on in the handout. Let's make it so that here on the computer it's saying the same thing. You can use the select button and double click on a junction, and it'll bring up a bunch of parameters about it, including its label. So I'm just going to rename the label. Instead of J1, I'll call it A. And then close that. You'll notice that the annotation has reflected the change that I made. Double click on junction B, and instead of J2, I'll update that to B. Now, I can be even more efficient than clicking on the individual junction locations. I can bring up a table. It's called a flex table. If you click on the flex table and indicate that what you want is the junction flex table, then it brings up this table where we could adjust the labels here. So for example, J3 is the one that should be C. J4 is the one that should be D. J5 is the one that should be F. And J6 is the one that I want to call E. Okay? Note that here in the junction table, there's some place that I could indicate the elevation at each junction. So in your project, every one of the junctions has a physical elevation that's different and unique because of the contour lines. In this example we're doing here and now, let's just assume that all of these are at an elevation of 0. So they all have the same elevation. I'm not going to change any of them, but in your project, the elevation you should put in for each junction is its actual ground elevation at that spot. Okay, so that's it for now with the junction renaming. If we go into the pipe table, so here the flex table for pipes, you'll notice that the pipes have names that are, I don't like those names, P1, P2, and so on. I'm going to rename the pipes according to their starting and stopping node. So for example, P1, I think it would be better if we called that pipe AB. P2, I'd like to call pipe BC. And so just changing all of the pipe names to reflect the junction. And then the ones that are connected to a reservoir, I'll call it like RA, from the reservoir to junction A, and then this other one I'll call it RD, for reservoir to junction D. So I've changed the names. The other things that we need to change include the diameter of each pipe. And so on the handout, for example, it says that the diameter of pipe AB is 500. Okay, BC 650, CD 850.
Is there a way to switch units?
Yes. Did your units come up as traditional units? Okay. Unfortunately, that means that you may need to start over. But let's just see. Maybe you don't. Okay, so go to Tools, and then More, Options, Units, and yours should maybe say Traditional, U.S. Customary, so switch it to SI. And once you switch to SI, maybe you don't have to start over. We might be able to get away with it. It's early enough. So again, to get there, it's under Tools, Options, Units, and then...
Flex table is still in standard units.
Okay. Well, the other move that we just might be able to make is if we go back into the flex table. You said it's still in those units. Go to the right-click on the column, Units and Formatting, and do you see the SI units as an option that you could choose?
Yeah.
Okay. So choose millimeters.
How did you click on the column?
Just at the top of it, right-click, and then Units and Formatting. Okay. But I guess I should have given you that warning at the first. It hadn't occurred to me that the default would be traditional units, but of course it is, right? So I'll make a note to myself for next year, check the units as the first thing that we do in this demo. All right, so let's continue inputting the pipe diameters. For the one that connects the reservoir, let's make it a really big pipe because I just want there to be essentially no head loss through that pipe. So I'm going to say 1,000 millimeters for the pipe that connects the reservoir to the pipe network. So it's a gigantic pipe. In the handout that I've given you, it says that all of the pipes have an epsilon of 0.3 millimeters. That so happens to be the equivalent sand roughness for ductile iron. But let me show you on these materials property. See where it says ductile iron? If you just click one of them, then you get this ellipsis next to the word. It's the 3 dots in a row. If you click on that, it brings up a materials library. And so if we expand that list and we look at what does it know about ductile iron, if you click on ductile iron, then down here it says the roughness height in meters. So 0.0003 meters is the roughness height. That is the equivalent sand roughness that we know applies to our network. So everything's fine for us saying it's ductile iron. It's going to get the roughness that it needs. You'll notice that it mentions the Hazen-Williams C. We can have the computer do its calculations in the Hazen-Williams method or the Darcy-Weisbach method. Does anybody remember which is more accurate?
Darcy.
Darcy-Weisbach's more accurate. So we don't care if it's hard for the computer to do its calculations. It's got plenty of horsepower to do that. So we're going to, in just a moment, go in and change it so that it, by default, uses Darcy-Weisbach equation and gives us the maximum accuracy. But the other thing we need to do is define the lengths of these pipes, because we've set their diameter, but not yet the length. So this column over here, it says has user-defined length. Click that on for all of them. And you're going to see when you click it, it's changing this length user-defined from yellow to white. Yellow means that we can't edit. If it's white, it means that we can edit. Okay, so now that we're saying we want the user-defined length, we can put in the lengths that we know for that pipe. So AB, for example, 220 meters. BC is 100 meters. And you may need to, again, go in and change the units. Right-click, units and formatting, and change it. If it was in feet, you can change it over to meters. But let's put in the known length for each of these. And for the AF, that's 180. For the pipe that connects the reservoir to the network, let's just make it 10 meters. We don't have any of that on the handout. But if we make it short and big, then it's not going to contribute to any losses, which is what we want for this model. Okay, so we've defined the length, and we've defined the diameter. We checked the roughness. We have to give it some information about the reservoirs. We need to tell it the elevation of the reservoir. Remember, the elevation at reservoir A and the reservoir elevation at D. So if we double-click on this reservoir, then it brings up the physical elevation. We want it to be 61.162 for reservoir at A. And if you're wondering, I think there is a reservoir junction table, so we could do it that way too. So 61.16 for reservoir 1. Reservoir 2 has a head of 57.83. We're getting good and close to ready to solve this model. Okay, I'm going to go into the options and force it to use the Darcy-Weisbach equation now. That's here under the Home tab at the top on the ribbon. Options, base calculation options, double-click that. And it brings up this little window, and right now the friction method is set to Hayes and Williams. Change it to Darcy-Weisbach. So once again, I got to that by going under Options, Steady State EPS Solver. So double click and then say that the friction method is Darcy-Weisbach. Okay? Now the only other thing we have to do is tell it where water's coming out. So if you look on the diagram, water comes out at E. Let me double click on E. And well, actually, let's do it through the junction table. So junction table, that's 150. If you'll give me one more minute, I'll give you 2 extra minutes to take the exam. All right?
5 minutes.
You can leave. All right. So what we want to do is we want to add a demand collection at E and B. So here at E, where it says demand collection, I'm clicking on that, and I know that the water that's going out at E is 1,600 liters per second. And then I need to define a demand collection also at B is 600 liters per second. Okay, so now the network knows, I think, everything it needs to know to be able to calculate. So I'm going to click this green arrow at the top, compute, and it's going to crunch some numbers. I may get some warnings down at the bottom. Let's see. No error messages. And we can double click on any of these junctions. So for example, we can double click on junction B, and it will give you the pressure at that location. So the pressure, 564 kilopascals. Or you can see the pressures through the junction table. So over here it's got the pressure at each junction. And if we go to the pipe junction, the pipe table, it'll tell us the flow rate through each pipe. So over here you've got the flow rate that's going through each pipe. So it solved the pipe network in the same way that we could have using the spreadsheet. All right, so it's 1:52. I will give you that 5 minutes. All right, that's it for today. I'll see you for the exam on Wednesday. And we'll pick this example up just in case you got hung up on anything. We'll revisit this example again on Monday of next week.